All right, so welcome everybody to our Monday seminar. Today, we are very happy to have with us Christian Bauer from University of Berkeley. He is actually the director of the theory group in the University of Berkeley in particle physics. And he's very well known among all of us as one who has been very often involved in the close connection between theory and data in particle physics. And today he's going to tell us about something very futuristic. So please, Christian, the floor is yours. Thank you.
Thanks so much. Well, it's great to be here. I actually am physically in Madrid, but you know, the situation, I guess, is it keeps coming back to this situation. Hopefully, at some point, I can come visit for real again, as I'd really much enjoy to do. Yeah. So what I want to tell you today is about some work that I've sort of started doing over the last few years, as you said, it's sort of futuristic, as in this is not something that will impact particle physics in the next year or two. But I think, and I'll try to convince you, this is something that's worth thinking about now. And, you know, as with most things, if we want something to happen in the future, we need to start, we can't think of it a year or two before we want it to happen. We have to start much earlier and really lay the foundation for this. And so let me start. This is, of course, a slide that you all know very well. It represents the standard model. And that is, of course, what probably most of us are interested in, either in understanding the standard model in more detail or to understand the shortcomings of the standard model. You know, we all know that the standard model, as we have here, has been incredibly successful at explaining essentially every experiment that we've done in particle physics, typically collider experiments. But we also know that it only describes a really small subset of what is going on in the universe, right? It's only describing about 4% of the matter or the energy budget of the universe. And so clearly we want to be able to understand and test this standard model with ever more precision to hopefully eventually find where the standard model fails and where it can start to explain dark matter, dark energy, and possibly many other things that are still puzzles in the standard model. Now, you also know very well how we do typically these experiments at the energy frontier, at least. We tend to build large colliders. This is the tunnel at CERN of the LHC experiment. And the goal that we have is we want to compare, we want to really understand if the standard model describes the data we observe at the LHC. Right? That's I think what in the end all of us are interested in, and whether we work on extensions of the standard model and try to predict what the LHC or other experiments might see as deviations from the standard model, or if we're more on the side of making precision calculations for the standard model. But I think the ultimate goal is always the same, to try to test the standard model. And clearly what we need to do in this, we need to connect theory on one side to data on the other side. And so we need to be able to go from Lagrangian to events that are actually observed at the LHC, for example. And what is typically observed is fully exclusive events, and this has been a real bottleneck in a theoretical understanding. While we can make sort of predictions for somewhat inclusive observables, to really make predictions for fully exclusive observables is quite difficult. And so I would say this is sort of one of the holy grails of high energy physics, is really the full simulation of a scattering process of colliders. So at the moment, the way we do this, we sort of use perturbation theory, and I'll go through this a little bit more in the next few slides, to make a prediction for the hard scattering, for which perturbation theory works very well. And then we use sort of all sorts of other approximations to the full physics, for example, parton showers, which is sort of based on a collinear and soft approximation of the process. And then we try to simulate sort of the hadronization of the event that is really long distance physics, and that we typically do with some models in that are sort of embedded in parton showers typically. Now, of course, what we try to do is we try to compare observables that are sort of less sensitive to some of these more murky aspects of our simulation. But nevertheless, there's always some sensitivity to it. And so it would, of course, be absolutely fantastic if we could really have a first principles calculation of that full scattering process at say, the Large Hadron Collider. So the dream in my mind would really be to literally compute the full S matrix of a scattering process. So what that would entail, it would entail to create an initial state with 2 protons at some early times. Okay, that's my initial state. Then I do time evolution according to the rules of quantum field theory, and really take the full standard model Hamiltonian, the full and do e to the IHT of that Hamiltonian and do time evolution with that. So what that time evolution operator will do, it will take the 2 wave packets of the proton, they will start move together. At some point they would collide, produce all sorts of high energy, high mass excitations, and then put out a spray of particles that then fly apart, and then they shower, hadronize. All of that is described in principle by that time evolution operator. And then we produce some final state X at some time T in the infinite future in principle. And the overlap squared of this object is the probability to measure a final state X given my initial state of 2 protons. So if we could do that, then we could literally compute the probability distribution for each final state, for a completely exclusive final state, and compare directly against the LHC. So then all we need to take care of is sort of detector effects and unfold those. So a couple of comments here. This sounds really great. Now, clearly, this problem requires quantum physics, right? The Hamiltonian that sits in here is based on quantum field theory. And, I need to somehow formulate this in quantum field theory. It should also be clear to everybody that this is not something that's even remotely feasible at the moment, right? I mean, nobody is trying to simulate from first principles a scattering process. We do perturbation theory. As I said, we use parton showers, all sorts of things. And we try to break this problem apart because it's just not feasible, even remotely, using any kind of known technique that we have. But I think probably most of you would also agree that if I could do that, it would totally revolutionize how I could compare experimental collider measurements with theoretical predictions. So in today's talk, I actually want to talk a little bit about, what can we do? Is this something that maybe with quantum computers might be in the realm of feasibility? And if not, what would be in the realm of feasibility with quantum computers? So the way I want to structure my talk today is I want to talk a little bit about general principles that you need. And here I talk about 2 basic theoretical principles that we need here in order to do the simulation. The first is lattice field theory, because I need to map this problem in quantum field theory, which is a problem of an infinite dimensional Hilbert space. I need to map that onto a problem that is a finite dimensional Hilbert space, so I can actually put this on a computer. So I'll talk a little bit about the lattice field theory aspects of it. And then I will show you that this problem that I just laid out to you, this full scattering process, is even on a quantum computer is really, really futuristic. And so what I will try to argue that if we can combine sort of lattice field theory techniques with effective field theory techniques that sort of separate short and long distance physics of a scattering process, then we might have the hope to actually do computations, first principle calculations on a quantum computer that really do teach us something about scattering processes, really ab initio scattering processes. Then I will tell you about one particular sort of first attempt at this that we did in computing a certain quantity, which I will define in the first part of the talk, a soft function that is directly related to a scattering process, and how we could compute that on a quantum computer. And then at the end, and you'll see in this part of the talk, when I show you sort of final result, you actually see that quantum computers at the moment are very noisy. And we do need to deal with, at least in the near term, deal with noise on quantum computers. And actually quite a bit of our work in Berkeley is on dealing with errors and noise in quantum computers. And I'll just give you a flavor in the last few minutes of my talk on the kind of work that we do there. Okay, so let me get started on the general principles. So I've already showed you this expression of the S matrix. And let's set the stage a little bit. Of course, all elements in this expression is determined in terms of some fields. So I collectively always write phi of x here. Now, of course, in the standard model, you don't have scalar fields typically, but you have fermion fields, gauge fields, and so on. Actually, for everything that I'm going to do in this talk, except for, I think, the last slide, will be about scalar field theory, just because that's the easiest version of a field theory. But the general ideas hold for more complicated field theories. The important part here is that phi of x, there's sort of two infinities, and that I don't mean renormalization infinities, but sort of two continuous things in field theories. The first is the position x, which is continuous. And then the value of the field phi is another continuous variable. So at every point in x, which is sampled from a continuous distribution, there is another field phi, which is also continuous. And so if I want to put this on a computer, I need to sort of take this problem and go from the infinite. So in other words, there's an infinite dimensional Hilbert space that I need to deal with. And the first thing I'm going to try to do is I'm going to take this problem and map it onto a problem of a finite dimensional Hilbert space, and essentially map it onto quantum mechanics problem, which then I will argue I can actually possibly tackle on a quantum computer. So in order to discretize space, that is something that has been known for a very long time how to do this. We essentially, instead of sampling at every possible point in a spatial coordinate system, we sampled at discrete points in my coordinate system. And that essentially means I'm putting down a lattice, a spatial lattice, and I sample things only on the lattice points. Now, in order to find a lattice, there's sort of typically two values that you have to specify. The first one is the lattice spacing, so the distance between two lattice points. Oops, sorry. Let me call that little L here. And then there's sort of either you can view it as the size of my lattice in each dimension, capital L, or you can say it's the number of lattice points per dimension, capital N. And of course, the lattice dimension, the lattice size is n times the lattice distance. I should warn you, I sort of switch sometimes between capital N and little nl. It's the same object. It's the number of lattice points per dimension. Then on each lattice point lives a quantum field. And I'm going to ignore right now that for gauge fields, they would actually live on links of lattices. So for this talk, I'm just going to talk about fields living on lattice points, which is the case for a scalar field theory. And now, instead of having continuous field at each lattice point, I'm going to digitize that and say that I'm going to only sample this at finite values of the finite field values. And so let me call the number of finite field values at which I sample the field n phi. So there's three numbers that really quantify my discreteness of the problem. And you can work out the Hilbert space as dimension. It's the number of field values per lattice point raised to the power of the number of lattice points. So it's n phi raised to the power of n to the d, because n to the d is the number of lattice points. But once I have this in this Hilbert space, everything, the Hamiltonian is a matrix. It's just a Hermitian matrix. The time evolution operator is just a unitary matrix. Okay, and so I could hope then to actually to solve the problem by matrix multiplication. So let's try to understand what are sort of the numbers involved in this. But before I do this, let me just quickly say, so essentially computing that S matrix would now be reduced to 3 steps. I create some initial state vector. So now my initial state, my final state are just state vectors in that Hilbert space, or just finite dimensional state vectors. I create that. Let's assume I can do that. Then I have the evolution operator, which is a matrix. I do a matrix multiplication of of that state with the evolution matrix, and then I dot it into the state vector of this final state X, and I take the overlap, gives me a number. The square of that number is the probability. Okay, sounds really easy. So what is the problem here? Well, the problem is the scales involved in the problem. So the energy range that can be described by a lattice is given, the largest energy is given by the inverse lattice spacing. And so you can very easily understand that if you think about, high energy means short wavelength excitations. And of course, if the wavelength becomes smaller than the resolution I have in my lattice, so which is the lattice spacing, then I can't resolve these high energy fluctuations anymore. So the highest energy or the shortest wavelength I can resolve is given by the inverse lattice spacing. Conversely, the lowest energy I can observe, or the longest wavelength I can see, is given by the size of my lattice. If my wavelength is like 10 times larger than the size of my lattice, there's no way I can see that anymore. I cannot measure that wavelength any longer. Okay, so the energy range that my lattice can get is essentially given, the ratio in ranges is given by the number of lattice points per dimension. So now you can say, well, if I want to simulate the full LHC, I want to go up to 70 EV, and let's just assume we're good enough. If we go down to 100 MeV, we have enough of sort of the non-perturbative physics. It's a little bit below lambda QCD. That's probably not true. You probably have to go lower than this. But let's take this range of energy as sort of what I need to do and try to see how big do these numbers become. Well, that means I need 70,000 lattice points per dimension, just the ratio of these two numbers. I have 3 dimensions, so that gives me 10 to the 14 lattice sites. All right, it's a pretty big number. And so let's assume that I want to have at least sort of 5-bit digitization. So that means I can sample at 32 field values. That seems like a small number, but it's actually been shown that the error is exponential, or vanishes exponentially as I raise digitization. So you can actually get pretty good digitization for relatively low number of field values. So let's take this number 32, but that means my Hilbert space, the dimension of my Hilbert space is 32 raised to the power of 10 to the 14. So not 32 times 10 to the 14, 32 raised to the power of 10 to the 14. And that is, for all intents and purposes, infinity, right? We'll never get to computers that could do matrix multiplication of matrices of that size. It's just clearly completely impossible to perform such a calculation. Okay, and that's essentially why this problem is not being considered, and why nobody's really tried to formulate field theory this way, right? You don't find this typically in textbooks, putting quantum field theory on mapping onto quantum mechanics. However, I'm going to argue now that maybe this is a little bit naive. Do we really need to simulate this full energy range like this and use sort of map it onto quantum mechanics in this way? Because after all, we know that a typical event at the LHC involves very different energy scales, right? There's high energy scales at short distances and where perturbation theory works well. So for example, if I have a typical event, I might have an underlying QQ bar goes to TT bar event somewhere that happens at short distances. And for that, perturbation theory works really well. There's many people who work really hard at making higher order predictions in perturbation theory. And we now have n squared LO is now totally standard. And n cubed LO is sort of now the state of the art that people are working on. And so that is really what, we don't really maybe need to do sort of a full ab initio simulation. Maybe perturbation theory just works fine here. But then there is sort of a medium energy scale where that essentially, where I'm describing how partons can radiate other partons off. So that is sort of what the parton shower in the end does in sort of traditional simulations. And then at some point I'll have a really long distance, low energy physics that sort of describes the radiation of soft particles and of hadronization and so on. And this is really where we have absolutely no idea how to really do, perturbation theory completely breaks down at this low energy. And so I can actually systematize this a little bit more. I can actually, and this is something that we understand quite well, but in a typical event at a Large Hadron Collider, you tend to have individual, a relatively low number of jets. So there's a certain number of energetic particles that are being produced in the hard collision. Hard collision is that yellow blob here, which happen at some scale Q. And then I have sort of collinear radiation that happens at this intermediate scale. And that sort of performs sort of a collimated jet of particles. And typically the mass of those jets are much lower than the energy of those jets. So let's call the mass of those jets mj. Okay, so there's, and then you can find that there's soft radiation that happens that sort of, neutralizes the color between jets and can sort of talk between different jets. And that typical scale is of order mj squared over q. Now, the important thing is that if mj, the mass of a jet, is much smaller than the energy of a jet, and as I said, this is what a typical event looks like in the LHC. Typically, what we're interested in the LHC, we have events that have this hierarchy of scale. And then the soft scale mj squared over q is, of course, also much less than mj. So we have a strong hierarchy of scales, that's sort of 3 typical scales in the problem. And we should try to use effective field theories to understand the separation of those scales. That's what effective field theories are made for. And that is, of course, something that we did do now over 20 years ago when I did my PhD. And then afterwards, in a postdoc at San Diego, we developed soft collinear effective field theory, which precisely captures that separation of scale that happen at collider events. We actually originally thought of it much more in sort of B physics area, but it was quickly realized that sort of probably collider physics is the more important application of soft collinear effective field theory. And soft collinear effective theory is now really widely used in all sorts of areas of particle physics, from a formal understanding to QCD, to understanding jet substructure, understanding parton showers. Lots of resummed calculation nowadays use soft collinear effective theory, but we also realized actually very early on that we can understand proofs of factorization from soft collinear effective theory. And that is actually what I'm going to use soft collinear effective theory for in this talk and for the quantum computing part. So the idea is that I can write a differential cross-section of a typical LHC event in terms of sort of a convolution of individual objects. There's sort of a hard object, and that is the object that characterizes the short distance process that happens. So in the figure that I had earlier, that would sort of characterize the QQ bar goes to TT bar event. Then I have individual jet functions that sort of describe how collinear physics is developing and how collinear radiation is happening within each jet separately. And then there is the soft scale that happens, and those jet functions live at that scale mj, which is typically much less than q. And then there's the soft physics that sort of can talk between all the different jets. And it's the soft physics that lives at the scale mj squared over q. So let's try to plug in some number. And the important thing is, if I have the individual ingredients, h, the different j's, and the s, I can assemble this back together, and I can make a prediction for a cross-section. That is really with all infrared physics. So that's a non-perturbative statement that I'm making here. And the corrections are given by powers of mj over q. Okay. So, if mj over q is a small number, then I can make a pretty good prediction here for these events. And in particular, it is non-perturbative. It's a non-perturbative prediction. So let's plug in some numbers, and let's say we have sort of order 1 TeV jets with order 100 GeV mass. That's a typical scaling that I have. That means that the soft scale, which is mj squared over q, is of order 10 GeV. So that's a typical soft scale I have in these events. And this is sort of where we realized and where we sort of took the hook into quantum computing, where we kind of realized, well, look, if I have a 10 GeV scale, then I have a much lower ratio of scales that I need to deal with, right? So now I need to have a lattice field theory that needs to describe scales that range from, say, 100 MeV to 10 GeV. Now that requires only of order 100 lattice points per dimension. So it gives me 10 to the 6 lattice sites. Okay, 10 to the 6 is a lot less than 10 to the 14. However, 32 raised to the power of 10 to the 6 is still, for all intents and purposes, infinity. Okay, and so this is why, again, nobody has attempted to compute soft functions just from first principles ever. This is still something where I use some models, or I try to separate maybe the sort of the perturbative physics that lives at 10 GeV from the non-perturbative physics that lives here, and I try to do measurements in one process and relate them to other processes. But the question that I'm going to ask in this talk: can we actually compute a soft function, a non-perturbative soft function from first principles, using this technique? Now, clearly a classical computer will not do it, because I can't do matrix multiplication at the scale of 32 where the dimension of the matrices are 32 raised to the power of 10 to the 6. But what we asked ourselves, well, how complicated would that problem be on a quantum computer? And that's where I want to go next. And I want to try to convince you that this is a problem that I think can be done in the not next year or not tomorrow, but maybe in 10, 15 years from now. That might be something that is feasible on quantum computers. So before I go there, I wanted to just pause for a second and see if there's any questions.
Well, I may ask one.
Yeah.
So, I mean, you have concluded that you could use a lattice of size 100 to the cube to do the computation as far as the separation of scales is concerned. And that is, of course, the kind of lattices that are used nowadays often to compute non-perturbative quantities. And you're starting with this Hamiltonian paradigm, whereby you're computing the dimension of the Hilbert space, and of course doing this computation in the Hamiltonian formalism is not something that people try to do. So is there some fundamental obstacle to computing the soft functions using standard lattice field theory in the Lagrangian formulation?
Yes. So the obstacle is that the soft function is inherently has massless particles in it. So inherently it requires Minkowski space. And all the way we get around, the way we turn in traditional lattice field theory, the problem. I mean, what we do is we turn into a statistical problem, and then we do a Monte Carlo simulation over configurations. But that is essentially requires me to go to Euclidean space. So it's essentially is the fact that I'm trying to really compute, I'm trying to compute dynamics, which cannot be done on traditional lattices in the traditional lattice formulation in Euclidean space. So that is so if you actually look back at the Hamiltonian formulation of lattice field theory, which encodes the dynamics, goes actually back to right at the beginning of lattice field theory, back in the 70s. It was done by Kogut and Susskind. But it was essentially never really developed much further, because it was realized that you can't actually use, you can't simulate this, because you actually have to stay in Minkowski space.
Okay, thanks.
Good. So let me continue a bit. And so I think one really, really important paper in this field of quantum computing was this paper that appeared about 10 years ago now in Science by Stephen Jordan, Keith Lee, and John Preskill, where they essentially showed that you can encode the Hamiltonian of a scalar field theory on a quantum computer with resources that are logarithmic in the size of the Hilbert space. Okay, so instead of requiring, so if you want to have a matrix that has an exponential dimension, you only need logarithmic resources, or another way of stating the same fact is you need resources that are polynomial in the size of my lattice and not exponential in my size of my lattice as on a classical computer. And essentially, this is the basic idea here that we're also using, but we needed to develop this for this effective field theory framework, because as I told you, while this is the idea that you could use literally the full scattering in principle, but I think, to get sort of 10 to the 14 qubits is still, it will not happen in the next 100 or 200 years, probably, even if sort of quantum computers keep advancing at the pace that we have seen. And so this is sort of what I'm showing you here. Sort of if I wanted to do a full simulation of the LHC, I would need sort of order 10 to the 14 qubits. And I believe this is not something that will happen in my lifetime, or probably in the lifetime of any person on this call. And so I think it is worth trying to think, whether we can use these idea of effective field theories and do something that is, maybe possible in sort of the time scale of like 20 years or something. And so that's where I'm going now. I already essentially said this, that we don't really need to do, there's no point in using a quantum computer for everything, right? If there's no point in using a quantum computer for a problem for which a classical computer already has a very good solution. And so short distance scattering, we have very good predictions of that process. So we don't really need a quantum computer to do that. So I think we should only use quantum computers, obviously, for those calculations that are not possible using known techniques. And for me, that is sort of the non-perturbative area, or the non-perturbative part of quantum field theories. And so this is why I want to combine quantum computing with effective field theories. And I'm trying to show you now that we can use a quantum computer with relatively, with much more modest resources to say, do a soft calculation. So the soft function, so the important thing of soft collinear effective theory is I showed you that factorization theorem, but the important thing is that I can do a true field theoretical definition of each ingredients of that option. That is really what SCT added to this factorization literature. And in particular, the soft function you can write as an expectation value of an operator, which is given in terms of some expressions in terms of fields. So these are called Wilson lines. They're sort of path-ordered exponentials of fields. So in a scalar field theory, we take this idea, or this form, and I take two of these for a dijet process, for example. I have two of these Wilson lines, and I need to compute the overlap from the vacuum to some final state X that contains a certain number of final state soft particles. So I need to really be able to do the dynamics here of the evolution that really produces on-shell particles, on-shell massless particles, and that's why normal lattice can't do it. So the reason it has this form can be sort of understood. Essentially, we have energetic particles, and the way energetic particles can interact with soft particles is essentially just through a color source, if you want, or a charge that moves at the speed of light through a bath of soft particles, and that's essentially what these Wilson lines here describe. So the fields here live along a light-like direction, and I'm integrating over that whole path at which these light-like particles can propagate essentially through that bath of soft particles. But the important thing is there's a quantum field theoretic definition of this object. So now I'm going to try to do is, can I map this problem onto a lattice and then give a lattice version of this? And can I develop a quantum circuit that would actually allow me to compute this? Now, I should say everything I'm going to do here is done in the language of scalar field theories. So I'm taking a path of scalar soft particles, and that is essentially just to keep the problem simpler and more manageable. We're working right now on extending this to gauge theories. There's no, in principle, thing that prohibits going to gauge theories. It just becomes a little bit more complicated because I need to deal with gauge invariance and so on. So let me try to understand what a Wilson line is on a lattice. So I told you a Wilson line describes a particle moving sort of along a light-like direction through space. And so if let's call this my collision point, and let's say I have a Wilson line that goes from this point along this path out to infinity along the light-like direction. Well, that means a Wilson line that moves in this direction on the lattice means, I keep hopping from lattice point to lattice point and have an exponential of a field at this point, but these points sort of get excited at different points in time, right? So I really move forward in time like this. The Wilson line moving in the other direction sort of moves in time like this. And that means my operator that I had sort of two Wilson lines sort of moves two excitations out in time along the lattice like this, as I'm illustrating here. In this graphic. So that means you can formalize this in field theory by essentially taking the field your Wilson lines and taking that, putting that integral, discretizing that integral, writing it as a sum. So I'm having a sum over field values where I'm putting the time equal to the position. So that means it's moving along a like direction. And then I can use time evolution. So that means each of these fields is sitting at a different time. And I can use time evolution to sort of move in between these different times. So essentially go to the Heisenberg picture. And that means I'm sort of alternating that this Wilson line operator is essentially given by exponentials of field operators at each different lattice sites, sandwiched between time evolution that tell me that there's a certain time that evolves between moving from one lattice site to the next. And of course, the time it takes to move from one lattice site to the next is exactly the lattice spacing, because it moves at the speed of light, or c times the lattice spacing. Okay, so that means I can write this object down in a field theory. And that means we can actually start to combine everything and create a quantum circuit that literally represents this whole object of this Wilson line. And this is what we did in this paper here, which was very recently accepted into PRL. So the idea would be we create on a quantum computer a vacuum state. It's the state in Hilbert space that is the eigenstate of the Hamiltonian. And it's the ground state. It's the lowest energy eigenstate of the Hamiltonian. Then I apply this object here, which is a unitary matrix. I multiply it onto this ground state. Okay, that's so this first operation here is creating sort of that state in my quantum system and on my quantum computer. Then I apply a unitary operator, that is that matrix element, and then I essentially perform a measurement on the system, or I do an evolution, an inverse evolution that sort of takes me from a state X back out, and I perform a measurement. And the square of that measurement, or the probability of measuring out a certain quantum state here, is equal to this non-perturbative object that I've defined here. So I'm not going to give you all the details of all these ingredients, but I want to give you a flavor of what goes into it. So the first thing is, I told you that for this object in here, we need the Wilson lines and we need time evolution in between these lattice sites. So time evolution in a scalar field theory is actually relatively easy. It was, as I mentioned, it was worked out in these papers, the first here, and then more details in some later papers. And so the short answer is that Hamiltonian you can do with polynomial resources on a quantum computer, and essentially everything boils down to sort of circuits that look like this. I don't know if you have seen quantum circuits before. So what this means, so each line here is a qubit. So it's a two-level quantum state. It can be either in a 0 and a 1 state. And for example, a box like this means you apply a rotation on my two-level state that is equal to e to the I times some phase times essentially the Pauli matrix Z. Okay, that's a rotation along around the Z direction. And an object like this is called a C-NOT gate, a conditional NOT gate. So that means you flip this qubit. So if this qubit here is in the ground state, you do nothing to this qubit. Whereas if this qubit, this Li qubit, is in an excited state, you flip this qubit from a 0 to a 1 or from a 1 to a 0. And now, of course, if this qubit is in a linear superposition of a ground state and excited state, you create a linear superposition of sort of the flipped state and the unflipped state down here. So the whole point is the whole Hamiltonian can be written essentially in terms of these gates here. And then we've worked out that the exponential of a field operator is even simpler. It's just given by just simple Z rotations on each of these qubits that represent my digitized field state. So, you know, I understand that you cannot follow really how we did this and what we did here. I'm happy to stay on and tell you a little bit more for those who are interested. But I think what I want you to get out of these slides that we can do this. We can essentially write a circuit that essentially implements this operator. So I can write a quantum circuit that essentially implements this unitary matrix. Okay. So then what is left to do is we need to have a quantum circuit that produces these ground states, right? These are also complicated states that I need to create. And it was worked out actually quite a while ago by Kitaev and Webb. So what we can use that essentially in a scalar field theory, the ground state is sort of a multivariate Gaussian distribution. It's all Gaussians, but with 2-point correlations in a field theory. So essentially the ground state takes some form like this, where this Gij is essentially the correlation length in the field theory, if you want, or the correlation matrix. And Kitaev and Webb have worked out an algorithm, or have given sort of a paper version of an algorithm that essentially can create, that can do this operation with polynomial resources. And actually in a recent paper a few months ago, we actually worked this out in much more detail and really sort of wrote down the actual quantum circuits required for this. It's a slightly involved algorithm, but it is true, it is a polynomial algorithm, and you can actually do this relatively efficiently, again, on a quantum computer. Okay, so we have this operation. The last thing we need is an operation like this. We not only need to create ground states, we also need to create excited states because we want to measure excited states. And in principle, this sounds very easy. Given the ground state of a theory, I can just obtain an excited states by acting with a creation operator on my ground states. The problem is the creation operator is not a unitary operation. So one has to be a little bit careful in how to do this, but this was essentially worked out in the seminal paper by Jordan, Lee, and Presko. You have to make the operation unitary, and you can do that by adding an extra qubit and essentially coupling to that such that the embedded excitation or the embedded creation operator then becomes unitary. And again, the complexity scales polynomial in the number of lattice sets. So that means we have written down, we have all ingredients we need to write this down, and it is indeed polynomial in the number of lattice points that I have. So now, so we could have said, okay, let's leave it at that. You know, this is a proof of principle. We have a paper version of the algorithm. Let's leave it. But I think one of the cool things about quantum computing is that there are actual devices that exist, right? A lot of these devices are actually built by companies. So IBM has quantum computers. Google has quantum computers. There's Honeywell has quantum computers. There's also dedicated companies that develop quantum computers. And of course, lots of universities are building quantum computers, and research labs all over the world are building quantum computers. So I think it is kind of prudent, if you develop a quantum algorithm, to actually run it on an actual quantum device and see if it works, even if the quantum devices, of course, are nowhere near big enough. You know, we need order million qubits to do something interesting. What we have available as sort of clean qubits are typically in the order of 10 qubits. Okay, so I cannot do this full calculation, but I can do a very simplified calculation on an actual device. And so what we did is we did the simplest calculation we could do. And essentially what this is, so remember, if I had my lattice here, I wanted something, a lattice that sort of allows me to jump between lattice sites. So the simplest version of a lattice that can encode the physics is 3 lattice sites. So I need at least one dimension so they can move. And I need at least 3 lattice sites so I can have one hopping from the center to the outskirts. And that's essentially what we did. We did a quantum field theory, we did a soft function on 3 lattice sites, and we did a 2-bit digitization. So we needed a total of 6 qubits. Okay. And so here is, now, the nice thing is in the simplified calculation for scalar field theory and so on, I can actually do this calculation analytically. Right? So I don't actually need a quantum computer to do this calculation. I can do it analytically, but of course that is very nice because I can check my quantum computer and see how well it does. So this is a computation here. This is so let me be very precise what I mean by analytical calculation. This is a lattice calculation, but with a full field, with a continuous field. And essentially I can write that matrix element in terms of coherent states of the harmonic oscillator if I'm careful. Okay, and that gives me some analytic calculation, some analytic result here. So what I'm plotting here, I should be clear, this is the transition rate. So this is this expectation value that I want. So it's the expectation value starting from the ground state of my field theory via this Wilson line operator, going to some excited state X. And I'm showing you two plots here, one where I'm going back to the vacuum. So it's a vacuum to vacuum transition, and a transition from a vacuum to one of the excited states that has one particle with one excitation. And what I'm showing you on the x-axis is the coupling constant. And essentially this coupling constant, if you remember in my Wilson line, you probably don't remember, but essentially what the Wilson line was is e to the I g times a field. So if g goes to 0, then the exponential goes to 0, then this whole operator becomes the identity. And then, of course, if I have no coupling, so in other words, it's the coupling of the energetic particle to my bath of soft particles. If there is no coupling, then my particle just goes straight through my bath, and my transition probability, it has to stay in the vacuum. Okay, and so that means at coupling g equals 0, I have 1 here, and I can't go into an excited state. But then if I turn on my coupling constant, my transition probability to the vacuum goes down, and my transition probability in excited state goes up. And the other thing that you can see here, that this is not a straight line, is also not a simple parabola. So this means it's a non-perturbative quantity, right? So this is not done by perturbation theory in G, but this is an all orders calculation in G. And it actually is some exponential factor in G that you get out in this theory. It's like a pseudo-cut factor. So this is the analytical calculation for a full, for a continuous quantum field. Now I can do also an analytic calculation for a digitized calculation. So this is now essentially doing my my quantum circuit by running it on a totally noiseless, not on a simulation. I simulate my, essentially I do my matrix multiplication on a classical computer, and then you get this yellow curve. And so that difference between the yellow curve and the blue curve, that is the fact that I'm only using 2-bit digitization. We can easily show that if I do 3-bit digitization, that curve will essentially lie already on that blue curve. So that is that statement that I made very early on in my talk, that I'm having exponential convergence with the digitization. But with the machines that we had available when we wrote this paper, we essentially could only do 2-bit digitization. So that's what we compared against. And so now I'm going to show you a run done on an actual quantum device. So it's exactly the same algorithm as what gave me this yellow curve, but now run on a quantum device, not on a simulated quantum device, or not on a classical device. And this is what we got out when we ran this. And so now I don't know how you view this, whether you're more an optimist or a pessimist. I think an optimist would say, well, this looks good, right? I have, as the same trend. So this should be compared to this yellow curve up here. We only did the vacuum to vacuum transition. So the optimist would say, well, look, this is the same trend. It kind of has the same feature as the yellow curve. It starts high, it sort of goes low, it sort of turns over, and then it becomes more linear later on. Whatever. A pessimist would say, come on, you're just totally off this curve, right? You don't even reproduce the fact that at zero coupling, the overlap should be 1. And so now the interesting thing is, as I told you, this green curve ran the exact same algorithm as the yellow curve, just on a quantum device. So this is all due to noise in my quantum system. And so when we saw this curve, we actually tried to say, well, let's try to correct for some of the noise that we know, and see what we can get. And what is the best we can do by trying to, eliminate some of the noise that we have through some techniques that we know of. And then when we do that, when we correct the quantum device, this is just noise, trying to reduce noise in the system through various techniques that I'll tell you a little bit about in the last few minutes of my talk, we could get these black points. And now these black points, I think, look really, really exciting. They lie very close to the yellow curve. And we really, I think, show that a calculation like this on a quantum device is actually feasible.
Can I ask?
Yes, of course.
So is the size of the boxes indicative of the errors that you estimate, or?
No, so, this is one thing that I find, no, this is just plotting the central value. So one thing that I find, and I've made actually a point in a recent talk, is that at the moment, people don't tend to display uncertainties. which I think is really bad. There's statistical uncertainties here, but they're vanishing. Now there's clearly systematic uncertainty, right? I mean, what I really should have done, I should have presented you a green point with error bars, with the error bars hopefully overlap with the real curve. And then on the black points should have error bars that are much smaller. Nobody really knows properly how to put systematic error bars on these things. So no, these black points have nothing, the size of the points have nothing to do with errors at the moment. And you know, I totally agree with that is unsatisfactory. And I think that's something where the community has to get much better at, because, you know, I'm always the first one to say that a theoretical prediction is only as good as the error bar you put on it. And so that means you can argue, and I would probably argue that these points are meaningless until we can actually put error bars on it. But that's what we have at the moment. So essentially, the quantum computer gives a good description of the analytical results, but we did have to do something to move from these yellow points to the black points. And let me pause quickly and see if there's any more questions. That's sort of the end of my physics talk. And so maybe let's give a quick conclusion here. I will have it on my final slides, but I think what I try to have you walk away with, that we really can do these calculations, that we do have the tools that can actually make these types of calculations possible. Of course, we're still talking far in the future, right? We need millions of qubits to do these calculations. We don't have that yet. We still have a lot of work we need to do to develop gauge theories and how to formulate them on a Minkowski lattice and so on. But I think what I want you to walk away, that this looks very, very promising, that we can get there. And after I pause for some questions, I just want to spend maybe 2 or 3 minutes to explain some of the techniques we actually did to move from green to black. But let me pause for a second, see if there's any more questions about the physics part.
Hello.
Yeah.
Hi, Christian. Very nice talk so far. So I would like to ask you, in the original quantum circuit you had, what is not too clear to me is how you impose this light speed propagation. I mean, once you go into the lattice, somehow you don't have a well-defined speed of light, right? I mean, you will have a particular dispersion relations with
yes,
sines and cosines of your field, but then
yes, so you have to be very careful. I agree. There's lots of subtleties here that I'm glossing over, that you have to deal with. I think for the purpose of this talk, what I essentially said is, we need the most important part is that we need to do, and of course we need to formulate this right, in the fact that the dispersion relations are different on a lattice and so on. But the important thing is that if I put an operator at this point here at time t equals 0, by the time, so if I have a field that lives here, an exponential that lives here, by the time my exponential touches these 2 points, my time has increased by a number L, which is the distance in my lattice points, right? And I need to take that into account. So I need to do time evolution between these 2 points. And then you're right, there's all sorts of subtleties how I precisely formulate and deal with the fact that dispersion relations are different. And we can talk a little bit more after, but I think that goes into a lot of details that I just didn't feel comfortable including here. But essentially, the main point that I said here with the time evolution, that is essentially the fact that I have exponential field operators, then have time evolution. Here, delta x is the same as little l, it's the lattice spacing. And then I have another exponential operator, time evolution again, and so on.
Okay, thank you. And let me ask some other thing, which was not totally clear to me. I think I understood at some point that you had that you are dealing with the free field theory all the time, but then I guess that the fact that all this Wilson line calculation that you are doing, then it will always be Gaussian, so it's always simple to calculate this on a classical computer, even if you have large lattices, right?
Not really. I don't think this is easy to compute on a classical computer. Even the Gaussian. So we have not, the scalar field theory on a lattice, yes, it is easy to do. But as soon as I go to a non-abelian theory, that is, maybe one theory I can still do analytically, although I don't actually know of anybody who's worked this out, but it is possible. So yes, so this theory on a lattice, we could solve analytically, because you're right, in the end of it is Gaussian, it's coherent states and so on. But I think once I have non-abelian theory up here, so the gauge bosons up here are interacting, I don't think it's going to be done any longer. Now, what is important though here is that the Hamiltonian that sits here is the free Hamiltonian. So in other words, the interaction between my fermion, at the end of the day, what I have is the fermion moving through bath of gluons. That's what I want to describe. An energetic fermion moving through bath of gluons. And essentially the coupling between the fermion and the gluons is included in these Wilson lines. Now, of course, there's still couplings amongst the gluons themselves, but essentially this Hamiltonian, if you want, is only the Hamiltonian of QCD. It does not need to include fermions any longer. And so that actually makes the problem significantly simpler.
Sure. Okay, thank you.
Any other questions? Okay, if not, let me spend maybe 1 or 2 minutes on the final parts, how we deal with errors in quantum computers. I just want to give you a very quick flavor on this. There are sort of 2 types of errors that you have in current devices and probably also in futuristic devices. And they're sort of classified in two parts. There's sort of a readout error, or sometimes called a measurement error. And that is essentially the error that happens when you measure something. So you should view this as you put a quantum state in a particular system with no error. So you put let's say I put my qubit into an excited state. And then when I measure it, I don't always find it in an excited state. Now the physics here, what can happen, for example, my thing could have just decohered and fallen from my excited state back down to ground state by the time I had time to measure it. And so I don't actually measure it in an excited state, even if I put it in an excited state. So this is not an error with my ability to put it in an excited state. I did that with no error, but it's the fact that the system, that in the time it takes me to do a measurement, something can happen. Okay, and those are typically the largest errors in current devices. They're ordered 10%. So 10% of the time, if you put a qubit in an excited state, you won't find it in an excited state anymore. Gate errors are the second type. Those characterize my inability to do precise operations on a quantum device. So if I say I'm going to do an operation, I say, I told you earlier, I'm going to do a rotation on my 2-level system by some exponential of a Pauli matrix, while the gate errors characterize how precisely am I able to do these manipulations of my quantum computers. And as you can imagine, there's errors in there. And actually the largest errors are on these operations that combine 2 qubits together. It's these C0 gates, these entangling gates. Those errors are order a few % on current devices. Okay, now the important thing is on readout errors, even though they're larger, gate errors accumulate. So the more gates you apply, the more errors you're going to make. And with a few % errors, if you sort of do order 100 of these C0 gates, you're going to have an order 100% error at the end of the day. Okay, and so you need to deal with both of these errors. And just so you get an idea of the readout errors, so what this matrix here is showing you, we tried this on a 5-qubit system. So I put my computer in some state, some state, and you can see on the diagonal, we have sort of numbers that are sort of, 80, 70, that's the percentage of times the system has stayed in the state after I measure it back out. So you can see, and if you analyze this a little bit more, the more excited states you have, the smaller the probability it becomes to stay, which is not so surprising. So you need to deal with these readout errors. And so we've actually developed recently a technique. So in the paper that I showed you, that was actually a dominant error. And we essentially just measured out this readout matrix, and I sort of, the first approximation, an inversion, a matrix inversion. It's not exactly what we did. We developed a different technique that's sort of based on sort of unfolding techniques and high energy physics, but the physics is, the idea is the same. You sort of just invert that matrix. We recently also developed the kind of cute technique, I think, is by sort of using active error correction. So essentially you entangle, instead of encoding of having a single qubit that has information right before you do a measurement, you entangle that qubit with, say, 2 other qubits. So that means if this state, so look, I'm putting 2 extra qubits on here. So that means if that state is in a 0, I'm not going to do anything to these 2 qubits. But if that qubit is in a 1 state, both of these qubits get flipped. And since they start in a 0, they're also in a 1 state. So after this operation, all 3 qubits are in the same state. They're either all in a 0 state or all in a 1 state. And then if I measure it out, if the probability is sort of order 10%, then the probability of 2 of them flipping at the same time is actually relatively low, right? It's the square of the probability of 1 flipping. And we can essentially do sort of active correction. So if you want, we can do a majority vote. So we measure this out and we assign the value of this qubit, whether we measured a 0 and a 1 based on what majority we measured on these things. Now, what you can see here, I need to apply more gates to my system in order to encode this. And so that only makes sense if my gate errors are much smaller than my readout errors. And so we've sort of shown that this actually really does work. So where this is, if I were to just take my nominal circuit and see what I get out, what the size of my readout errors is, if I do this encoding, I get a much smaller uncertainty. And you can see, you can understand sort of that the improvement really depends on the relative size of gate errors versus CNOT errors. So that is sort of techniques where this is something that we did just a few months ago about readout error. And here's a technique that we have various techniques on the gate error mitigation, but this is a technique which I thought I was quite surprised how well we could do on this. This is actually a chemistry problem. We measure the local magnetization of some molecular system. And so we did some time evolution as a function of time. So we need to do time evolution. And by the time we get to the end here, we had applied, I think, order 200 CNOT gates. Now, each of these CNOT gates has an error of about 1%. So, and the original circuit, if I don't change if I don't do anything to my errors, you essentially see the magnetization just gets 0, which is random. It's random magnetization. That is essentially because the errors in my quantum system are now 100%, and I essentially get just a random result out. However, if we actually do some of these error mitigation techniques that we developed here, and you can really recover. So black here is an analytical calculation, and the red is if we sort of combine various techniques that we developed in these 2 papers together, you can see that we can sort of recover a lot of information from this blue run. So the blue run is what I did on my quantum computer, and then essentially just did classical post-processing to turn these blue results back into red results, which show very good agreement with the analytical curve. So I think all I want to hear you for you to get a flavor that we really need to do error mitigation on these current devices, but that we can do this actually quite successfully. You know, that this is also a lot of active research going on. Okay, so this brings me to the end of my talk. I hope I've shown you that there is a lot of things we can do on quantum devices, and that I think in the future, not in the immediate future, but 10, 20 years down the road, we might have the possibility to really do really exciting first principles calculation that are truly non-perturbative on these quantum devices. There's lots of things we need to do. We need to think about scale. We've done everything in scalar field theory. Obviously, need to think about gauge theories. I've not talked about renormalization at all in this talk, which obviously we have to do once we go on to lattice. That's something we need to do. I just want to flash one slide on gauge theories, such that at least you can see that we're thinking about this. This is a plot from a recent paper that I wrote with Dorota Grabowska at CERN, where we sort of have a new formulation of a lattice U1 gauge theory, where we have a much better understanding of, here we show sort of our work, the error essentially in our work compared to previous works. And, if you compare to this work, we have much better understanding of the uncertainties of what is going on here. So this is just an advertisement slide. Obviously, I'm not telling you what we're doing here, but just more that we're working on gauge theories. And I want to leave it with sort of a roster of sort of all the people who've contributed to quantum computing in Berkeley, which come really from different areas, from computing, from chemistry. These are undergrad students, graduate students, postdocs, faculty. So it's a pretty wide range of people, and it's really exciting to be in this field. So I'll leave it here. Thank you.
Okay, thank you, Christian. That was a very nice talk. So other questions for Christian?
Yes, I think I have a couple of questions. Well, thanks again for the very nice talk. When you were discussing this error mitigation techniques, at some point in this readout where you were applying these 2 additional C nodes, I mean, it looks somehow similar to this repetition codes in quantum error correction, but then it's what I don't understand is that since you are measuring just right after the C node gates, what is the difference between this type of technique and just repeating the state preparation and measurement 3 times in a row and not using ancillary qubits, but just the same circuit 3 times?
Because you only get a statistical. So what you get if you do this multiple times, you get a statistical understanding of what's going on. Whereas here you get for one event, you can do an event by event correction here. Right, so I will know for this one circuit. So what we've done in the past, and this has worked, right? I mean, I've showed you the plots that it works very well, that I can statistically, I know the probability if I do this measurement, the probability of this state being something else is this, and I can measure this. There's actually one issue here. If you, so, essentially we measure out this matrix and then I just statistically correct. I do many measurements. Statistically, I can correct. There's 2 comments here. First of all, this matrix has exponentially many entries for the number of qubits. Okay, so if my goal is to have quantum supremacy, I cannot do this. So if I'm at a level where my classical computer, where the dimension is so big that classically I cannot handle this anymore, I cannot actually do this matrix inversion. Okay, so that's the first thing. So the statistics just doesn't work anymore. And the second thing is here, I can really do this on an event by event basis. So if I actually want like a real event simulation, that I want event by event to get a prediction, not a statistical average, then I think this is a more promising technique.
I see. Okay. And the other thing was also related
by the way, this is exactly repetition code. So the main difference though is to the normal error correction is usually what I do is I try to encode the entire circuit like this. So every operation I do in my circuit, I now do on these 3 qubits instead of 1. And that of course makes the problem incredibly hard. There's many extra C knots added. And essentially full repetition code, a full error correction, you need much smaller error rates on your C knots than you currently have. So the idea that we had here is to only apply to the readout.
Yep. So related to this, the same question is, this circuit is somewhat specific to only having qubits, or you could generalize it to any digitization, as you call it, of the scalar field? And the fact that you use these C nodes, does it work for more?
You mean this? Yeah, no, the way you would do this, so this, you should view this as, so how should you read this? I'm having a circuit that has, and I'm just showing you 1 qubit in that circuit. Okay, so the way you would do this on our circuit, so imagine now you have a circuit of, I mean, these are even registers of circuit, right, of qubits. So each one of those is multiple qubits. Now on every qubit in my final state, I replace each of these qubits with 3 qubits, encode it like that, and then measure it out. So you would encode this, and that's of course why it is also hard to do, because we don't have that many qubits that are all connected to others. But yeah, so the idea would be at the end of your calculation, let's say you have 10 qubits for your whole calculation, every one of those 10 qubits you now encode into 3. So you use
Okay, thank you very much.
More questions? Can I ask a couple of clear ones?
Yeah.
About this business of the measurement. I thought that you were after the soft function is a function of the end state, and it's itself a probability distribution, S of X, the probability distribution. So you will have to measure many times in order to determine.
Absolutely, yes.
So you will have to run the experiment, the simulation, a number of times, which is exponential in the number of outcomes that you want.
Well, see, no. So that is where it's interesting. So that is an interesting fact. That is, you know, I remember being really confused about this at the beginning. So if you think about it, take a parton shower simulation, right? For an LHC, we have hundreds of possible. I mean, or even just take the LHC, right? So there's hundreds of particles in the event. The number of possible outcomes is exponentially huge. But the statistics with measuring a certain observable does not grow with the exponential. It's still 1 over square root of the number of measurements I make. So in other words, I'm literally, so what this would allow me to do, it is directly sampling from this probability distribution, right? So if I do this right, I set this up in the, so the way you should do it, the way you should think is I start from the ground state, I evolve, and then I just measure out a state, and I will get, you know, this will evolve in the most likely state. So I mean the amplitude, so put it this way, this evolution, oops, sorry. So after, forget about the X for a second, the state that I obtain after acting with this operator T, or this unitary operator on the ground state is a linear superposition of all possible states with amplitude, well, with the correct amplitude. Okay, and then if I perform a measurement, I get the right state out with a square of that amplitude. Okay, and so that means the probability distribution with which I obtain a given event is exactly the quantum field theoretical definition, namely the square of the amplitude of that quantum field theory amplitude. Okay, so now of course, if I want to map the full, every possible soft function, so the way you should do this, I should now bin this result in the same way as an experimentalist bins his or her result. Okay, and then the statistic, and then the error of that binned histogram will be statistical in nature. Namely, it goes like 1 over square root of n of the number of measurements I'm doing on my quantum computer.
So you will coarse grain the readout.
Yes, so at the end of the day, I do have to bin my result like any.
The things you really want to know, and not the whole possible set of.
Correct. So if your goal would be, let me, you know, yeah. So the way I envision doing this, it's like an event simulation, like an event generator, right? I literally, I run my quantum computers, I don't know, 1 million times. And either I write these 1 million events out, you know, the classical results that I measure at the end of the day, the kinematics of this event out, but then I need to bin that result into a histogram. Of course, if I bin this finely enough that I have only 1 event in each bin, then I have 100% errors, right? So I need to do enough measurements that I have statistics that goes like 1 over root n. But it goes like 1 over root n of that measurements.
Another question. In your early estimate at the very beginning, you consider only 5 field values. Okay.
Yes. Sorry, 5 bits, so 32 field values. That's what I have.
32, okay.
Same thing.
I'm worried about the fact that, I mean, that's just an academic kind of estimate, but you were very worried about getting a sufficiently fine grained lattice so that you can get all the soft scales that you want, all the wavelengths of interest. But if you have a quantum field, the typical fluctuation of the quantum field scales with the inverse of the wavelength of the fluctuation. So if you want to have lots of wavelengths which are pretty soft, you will need a sufficient fine-grained division of the field values in field space so that you can accommodate that. Otherwise, your field will be frozen more than the physics of the problem requires. Okay?
So let me say it this way. So imagine for a second, which is not what we're doing, but I would formulate the theory on the momentum lines. Okay, so now every lattice point would correspond to a particular momentum of my field. Then I would say, so what you're saying is, yes, I do want to be somewhat fine-grained in the momenta, but the graining in which momentum states I do is given by how many lattice points I have. So if I were to formulate it on a momentum lattice, then the way you should think of the number the 32 that I'm saying is, what is the occupation number I put on a given field, right? Because it's like, you know, each one is now a harmonic oscillator with a given wavelength, with a given momentum. And essentially my 32 is how many excited states do I allow my harmonic oscillator to have? What is the occupation number? And essentially, if I make my, now of course, if my lattice is, so essentially the question is, in a realistic simulation, how many, you know, how many states do I get that have the exact same momentum given my resolution that I have? And I think the argument is that that number scales, you know, you don't have events, if you're sufficiently fine-grained, like with even 100 lattice points, I think you won't get to like 32, an occupation number of 32 of a fixed momentum, right? So the momentum graining is given by my size of my lattice spacing, whereas the 32 that I have here, the field digitization, is really the occupation number. And that is a number, and you know, you can prove this from first principles. Is essentially, you can, for example, you can prove on a harmonic oscillator that, you know, I could do the same problem on a harmonic oscillator, take a harmonic oscillator, and the question is, how well do I get my ground state of my first? So essentially, the argument is that the eigenvalues, or the physics that characterize the low excitations of my system is exponentially precise with the number of excitations I put on. And so as long as my system is such that I only care about low number of excitations, but by that I mean occupations, right? Not my field, not my momentum spacing, but my occupation number. As long as I only care about low number of occupation numbers, the value of the occupation number, I get very precise. It's exponential with the number of things I include in my harmonic oscillator. I know it's counterintuitive a little bit at the beginning. I totally agree with you.
Okay, so are there more questions? Not, most people left already, so I will stop the recording.